Since the 1980s, work has been done on blended wing-body aircraft. That is an aircraft with a relatively square central fuselage instead of the usual cylindrical fuselage. The main reason for doing this is to reduce the wetted surface, the total external surface of the aircraft. In a commercial airliner, roughly 50% of the drag is from skin friction drag. That is the air physically being scraped over the fuselage of the aircraft. If the area is reduced, then the total drag is reduced. The other factor is wing loading. Wing loading is the weight of the aircraft divided by the wing area, or more correctly, the effective wing area. By having the central fuselage also as an aerodynamic shape, that increases the total wing area and reduces the total wing loading. The wing loading has to be balanced by the lift of the wing, and the lift of the wing is a function of the mass density of the air times the velocity squared, which can be looked at as the Mach number squared, the area of the wing, the effectiveness of the wing, and then factors such as the angle of attack. For a commercial aircraft, Mach 0.85 is about the highest effective Mach number. Above that, you start getting into severe compressibility effects. The speed of sound is roughly constant from 35,000 feet to 60,000 feet, which means that the speed of the aircraft is also constant. If there is a lower wing loading, then the wing loading can be balanced at that velocity, which is about 540 miles per hour, 800 feet per second, at a lower mass density of air, which means a higher altitude. That lower mass density of air means less friction and drag on the aircraft. For a passenger aircraft, the blended wing body is problematic. There's no place to put windows. It's difficult to load and unload passengers, and in an emergency, the evacuation of the passengers can be problematic. Another problem with the blended wing body is that the upper and lower surfaces are flat planes. When you pressurize the interior of the aircraft so that passengers can survive at altitude, those upper and lower surfaces bend, and those bending stresses are bad in terms of material strength and fatigue. A cylindrical fuselage only has hoop stresses. It's all in tension, and that is much better in terms of material properties. But for a cargo airplane, the cargo could be put in three tubes. The tubes would be pressurized, and the rest of the aircraft would be unpressurized. The central tube would be extended to provide a crew area and a cockpit area. So the cargo would be shipped in a pressurized hold, but the bending stresses would be avoided. The cargo could be shipped in objects that are the size and shape of a 40-foot cargo container. You wouldn't want to use a standard cargo container because if the aircraft should, for any reasons, go to a high angle of attack, the cargo can shift backwards, and that shifting of weight could put the aircraft outside of its operational center of gravity, which would mean the airplane would then destabilize, fall out of the sky, crash to the ground, explode into flames, and everybody on board would be killed. The cargo containers would have to be partitioned, either with permanent walls down the length of the container, with the access to the container being on the side of the container, or if you want the access doors to be at the back, as they are with the standard cargo container, there would have to be a series of gates down the length of the container. So some cargo would be loaded, a gate would be closed and locked, and some more cargo would be loaded, another gate would be closed and locked, and so forth, till you get to those last doors on the container, and they're closed and locked, and that would prevent the cargo from shifting. A standard 40-foot container is about 40 feet long, 8 foot wide, 8 foot high, so it has about 2,500 cubic feet of volume. If the airplane weighs 450,000 pounds, and the airframe weighs 220,000 pounds, you have 220,000 pounds, roughly, for fuel and cargo. If you had 150,000 pounds of cargo and 70,000 pounds of fuel, which is a relatively shorter range flight, each container would have 50,000 pounds. You have 2,500 cubic feet per container. The density of the cargo could be 20 pounds per cubic foot. Fresh water, for example, weighs 62.4 pounds per cubic foot. Most cargoes are relatively high density, and so that shouldn't be a problem. There are airlines that fly cargoes, such as fresh flowers up from Colombia. Those are such low density cargoes that this design may not be able to efficiently ship them. At the back of the tubes, a hemispherical closure would be the most structurally efficient shape, but that could not be accommodated in opening the door. There would be no place to put it, so it would have to be flattened. Ribs can be added on the inside to reduce the total stresses and fatigue of the material. The entire rear door would be hinged to open upwards. On the outside of the aircraft, there would be doors similar to landing gear doors that would open to provide access to the tubes, and when closed, would provide the aerodynamic surface on the outside of the aircraft. For loading and unloading cargo, a vehicle can be slid in to the back of the tube, the container can be pushed out on top of the vehicle, and the vehicle can then lower the container to the ground for additional handling. For the military, those 40-foot containers are very efficient. They can be handled the same way you would handle a standard 40-foot cargo container. They can be placed on a semi-trailer and driven anywhere they need to be driven. Additionally, for the military, there would be cross tubes between the main tubes. This would enable pallets or platforms with workstations to be installed, and then personnel can man those workstations, and the aircraft can be used for electronic warfare or other missions. The fact that it's divided into 3 separate rooms does make it somewhat less efficient, but it can probably still be made to work. Antennas can be mounted in pods on the outside of the aircraft. That does represent a significant increase in aerodynamic drag, perhaps even 10%. Conformal antennas would have a much lower aerodynamic drag, but they're much harder to build and properly install. For radar, AWACS aircraft, the antennas would have to be stored horizontally for takeoffs and landings, and then rotated 90 degrees downwards for operations. The antennas could be rotated more than 90 degrees if the airplane is going to be in a constant circling turn. But the two antennas have twice as much aerodynamic drag, twice as much weight, and produce twice as much aerodynamic forces on the airframe. Additionally, if the antennas can't be transferred to the horizontal position, the aircraft can't land. So the antennas would have to be jettisoned. And if you couldn't jettison the antenna, then the plane crew would have to put on parachutes, bail out of the airplane, and let the airplane crash. Additionally, for the military, the tube spaces could also be used to fly pickup trucks, Humvees, tactical vehicles, and 155mm and 105mm towed artillery pieces. Ramps would be needed to move the vehicles to the ground. The ramps and cargo handling equipment for the containers could be flown in on a C-17. If you wanted to try to carry a truck in the tubes, it would have to be completely rebuilt. A military truck is about 11 feet high. The space in the tube is only about 8.5 feet high for a container. So the truck would have to be lengthened, the engine would have to be moved back, the bed would probably have to be shortened, the cab would have to be lowered. There wouldn't be enough room on the side of the cab for a door large enough to climb in. So a side door would have to be opened, and then a hatch on the top of the driver's cab would have to be opened as well, and the crew members would have to crawl down into the vehicle, the truck, which means overall, you're better off just shipping trucks on the C-17. For a military aircraft, a refueling boom could also be fitted, and it could be used as an air tanker. Additionally, as another military function, the tubes could be opened in flight, and the aircraft could be used to do airdrops. You could also drop things like bombs and cruise missiles at the back of the aircraft if you fit a suitable ejection system or delivery system to move the bombs and the cruise missiles out the back of the aircraft. The lower wing loading also means the aircraft could take off and land on shorter runways. The one question that does have to be carefully considered is stability in the y-axis. That's the pitch axis. That's the front of the plane going up relative to the back of the aircraft. Eric Brown, the British test pilot who is credited with having made the most aircraft carrier landings in one lifetime and having flown the most different types of airplanes of one person in one lifetime, said that the only tailless aircraft, an aircraft without a horizontal stabilizer, that flew well was the Me-163, which was the German rocket fighter of World War II. He said he flew about 5 other tailless planes, and he thought that every one of them was trying to kill him. The problem of stability and control is not a simple one, and if it can't be addressed, this aircraft can't work. The engines could be mounted at the back of the aircraft above the fuselage, with the vertical stabilizers canted somewhat outwards. That would mean that a significant part of the noise coming out of the back of the engines would be reflected off of the top of the aircraft and off of the vertical stabilizers upwards, reducing the noise signature at ground level. A specialized platform would have to be built for access to the engines, but it can be done. It is possible to make the equipment for handling containers and vehicles self-deploying. The equipment would have to be stored in the same tubes that hold the containers. It would have to be rolled out partially out the back. Wheels on long legs would have to be extended downwards to support the one end, the outer end. The rest of the equipment would have to be moved to the back of the container. A cable would have to be attached on the near end. And as it comes out, the cable would hold up one end while the wheels hold up the other. The cable would be lowered. The wheels would retract. The entire equipment would then lower to the ground. For handling vehicles, a tray can be put on top of the handling equipment. The vehicle can be moved back onto the tray. A cable can be attached to the vehicle so it doesn't roll off. The entire upper part of the equipment can rotate downwards at an angle. The tray can be slid downward to the ground. the cable holding the vehicle can be unwound until the vehicle rolls down onto the ground. It is a lot easier just to fly the equipment for handling vehicles and ramps on C-17s. The tubes could also hold 40-foot trailers for moving the 40-foot containers. You could put a trailer in each of two of the tubes, and in the third tube, you could have tractors. The tractors would have to have the same design, the same kind of awkward design, the low cabs, the awkward door, the top hatch, further shortening the back of the entire vehicle, and adding the fifth wheel, the turntable, for operating the 40-foot trailers. And so you could have two trailers and two tractors on each aircraft. The other piece of equipment that is needed is something to pick up and manipulate the 40-foot cargo containers. One option is to have a 40-foot rack that fits on top of the containers and picks them up. That rack could be mounted on top of the vehicle to which it would be attached inside the 40-foot tube. You would also need a forklift. The forklift and the vehicle with the 40-foot container would come out. The forklift picks that 40-foot long rack up off the top of the vehicle. The vehicle comes around, makes a 90-degree turn, make all the attachments, and now you have something that can lift and move the 40-foot containers. And once again, it is a lot easier just to fly it in on a C-17.